In this video, I will hand calculate the UV-Vis spectrum of a transition metal complex with a octahedral point group. In a different video, I showed you how to determine the atomic term symbols of the D2 electron configuration. There are 5 of those: 1s, 3p, 1d, 3f, and 1g. The numbers in the superscript are spin multiplicities, and the letters are the symbols for the angular momentum quantum number. So when we have L equals 0, 1, 2, 3, 4, we have symbols S, P, D, F, G. It took me 25 minutes to determine those atomic symbols for the D2 electron configuration, because I had to write out the 45 microstates of these 2 electrons and then group them carefully into these 5 atomic terms. So today I will show you a trick on how to determine the atomic term symbols quickly. If you have 2 s electrons, the atomic term symbol is 1s. If you have 2 p electrons, it's 1s, 3p, 1d. If you have 2 d electrons, 1s, 3p, 1d, and then 3f, 1g. If you have 2 f electrons, it's 1s, 3p, 1d, 3f, 1g, 3h, and 1i. You might have seen the trend. So basically you just need to write S, P, D, F, G, H, I, and so on, and then put a number 1 in the superscript first, and then for the second symbol write 3, and then 1 again, 3 again, 1 again, 3 again, 1 again, and so on. So the next one is 3k, followed by 1l. You may wonder, why do we skip j? J is used as the rotational quantum numbers for the rotation of molecules. So after I, we skip j, and we have k, l, m, n, o, and then we skip p because p is here already. So basically this is a very simple way to determine the atomic term symbols for S2, P2, D2, F2, and if you want, G2 electron configurations. For G2, you simply just again put 3k and 1l after this 1i. So enough about this atomic term symbols. Let's look at the 5 d orbitals. So first I want to show you this dz squared orbital and the dyz orbital. These two are on the same yz plane. And then these two are on the same xz plane. These 2 orbitals are on the same xy plane. So dxy, the x squared minus y squared are on the same xy plane. So this is actually important. That means if you have 2 electrons, one in dyz, one in dz squared, they feel larger repulsion from each other than if you put one electron in the dz squared and the other in the dxy orbital. Only because this dxy orbital and this dz orbital do not share the same plane. Similarly, if you put the 2 electrons, one in here, dxy orbital, the other in the dx squared minus y squared orbital, there's a larger repulsion between these 2 electrons. Then if you put the 2 electrons, one in here and one in here. Again, it's because these 2 orbitals are not in the same plane. Similarly, the repulsion between these two orbitals are less than the electron-electron repulsion between these two. Alright, enough about that. So again, in an octahedral structure of a transition metal complex, ML6, if M, the transition metal, has 2 d electrons, we have 5 different atomic term symbols. I crossed out 1s, 1d, and 1g for a reason. The lowest energy atomic term symbol is 3f. This is because in this 3f atomic term symbol, we first have a maximum value of the spin multiplicity, and then we have a maximum value of the orbit multiplicity. We have the largest s equals 1, 2s plus 1 equals 3. That's the multiplicity. It's a triplet. And we see this f. F means L equals 3. So we have only 3p and 3f atomic term symbols with the largest spin, and this f has a larger L than p. And then we know that the transition from a triplet to a singlet is called spin forbidden. We will only look at the transitions between 3f and 3p. In particular, we're going to look at the excitation spectrum. Therefore, we'll just look at the transition from 3f to 3p. First, let's look at 3p. 3p becomes actually 3T1G symmetry in an octahedral structure of this transition metal complex. And if you have an atom, it has a spherical symmetry. Now this atom is surrounded by 6 ligands. The symmetry is, the spherical symmetry is broken. Now we have a slightly lower symmetry. We call that octahedral symmetry with this 3T1G symbol. And this 3T1G symbol corresponds to putting 1 electron in the T2G orbital and 1 electron in the EG orbital. In particular, it's this: 1 electron in the dxy orbital, the other in the x squared minus y squared orbital, or 1 electron in the yz orbital, the other electron in the dz squared orbital, or 1 electron in the zx orbital, the other electron in the dz squared orbital. So we have 3 possible arrangements for these 2 electrons, and they have something in common. These 2 orbitals are in the same plane, the xy plane. These 2 orbitals are also in the same plane, the yz plane. These 2 orbitals also are in the same plane, the xz plane. Therefore, when we look at these arrangements, they have larger repulsion than the other 7 arrangements we can have. Why 7? If you look at F, F tells you L equals 3. S, P, D, F corresponds to L equals 0, 1, 2, 3. And then when L equals 3, you have M sub L equals negative 3, negative 2, negative 1, 0, 1, 2, and 3. M sub L may adopt 7 different values. Therefore, the orbit multiplicity is 7. So we should be able to have 7 arrangements here. So first, we can put the 2 electrons both in the EG orbitals. We have 2 different EG orbitals, dz squared and dx squared minus y squared. So they are here, dz squared, dx squared minus y squared. These 2 orbitals are not in the same plane. Therefore, the 2 electrons in these 2 orbitals feel less repulsion from each other. And also, we may have this T2G. So in this case, we also put 1 electron in the T2G orbital and 1 electron in the EG orbital. However, we do this a little differently. So, for example, we put one electron in the dxy orbital, the other in the dz squared orbital. So if we put one electron here and one electron here, again, these two orbitals are in general perpendicular to each other. They don't share the same plane. Therefore, this two has less repulsion than between these two. Again, this two has a larger repulsion because dxy and dx squared minus y squared share the same plane. Similarly, we can put an electron in the yz orbital and then another electron in the xy x squared minus y squared orbital. So one here and another one here. These two orbitals again are perpendicular to each other. They do not share the same plane. Therefore, these two electrons feel less repulsion from each other. And then finally zx and x squared minus y squared. So these two, they are also perpendicular to each other, which results in less repulsion. Okay, we can also put the two electrons in the T2G orbitals, and then we have dxy, dyz. They are perpendicular to each other, yz and xz, xz and xy. Again, they are perpendicular to each other. Therefore, the two electrons feel less repulsion than these three cases. All right, so that tells us we're going to see 4 different energy levels. And experimentally, yes, we will actually observe 4 different energy levels. And then we're going to do some quantitative analysis. And before that, again, I want to emphasize 3p has a higher energy than 3f due to larger electron-electron repulsion. And why is that? Again, in the 3p case, if you look at the 3 different arrangements here, the 2 electrons occupy 2 different orbitals, but these 2 different orbitals share the same plane. Again, these 2 share the xy plane. These 2 share the yz plane. These 2 share the zx plane. Therefore, there's a larger repulsion in the 3p term. Okay, again, experimentally, we know 3p has higher energy than 3f. And then I think it's Racah proposed some empirical models to quantify the difference. The difference is 15b, and b is typically 1,000 wave numbers plus minus 300. Well, b may change. The value of B actually depends on the nature of the ligands. So we'll talk about that later. There are 3 Racah parameters, A, B, and C. A is just the average electron-electron repulsion, and B accounts for additional electron-electron repulsion if the 2 d electrons share the same plane. And then there's another, the third parameter C, that accounts for the spin, electron spin. All right, so again, this 3p has higher energy than 3f by 15b. So we're going to put 15b here. But then you can see I have this equation, the energy of 3p, that becomes 3T1G, so 3T1G. In the octahedral environment, there's a second term, delta O. Why it's 15b plus delta O? Again, this delta O is the splitting between the EG orbitals and T2G orbitals. The EG orbital has higher energy than the T2G by delta O. This is the splitting in an octahedral environment. Why 1 delta O? So if you look at this 3p, it becomes 3T1G. We have 1 electron in the T2G orbital and 1 electron in the EG orbital. We're just looking at the energy difference between this EG and the T2G. By putting 1 electron in the EG orbital, we have additional delta O, that amount of energy. then putting the 2 electrons, both of them in the T2g orbital. So we have one additional term here, 1 times delta O. There's 1 delta O because there's 1 electron in the Eg orbital. All right, now let's look at this 3A2G. This 3A2G originates from 3F, so it's here. We have 2 electrons, both occupying the Eg orbitals. One in the dz squared orbital, one in the dx squared minus y squared orbital. So both are Eg orbitals. Therefore, we have 2 delta O here. But there's no B term. Again, this is because this dz squared and dx squared minus squared are perpendicular to each other. They do not share the same plane. Therefore, the electron repulsion between these 2 orbitals is smaller than the 3p cases by 15b. Therefore, we don't have 15b here. And then if we look at 3T2G, it also originates from 3F. And then this time we have 1 electron in the Eg orbital. So therefore we have delta O here. But again, there's no B term, only because these 2 are perpendicular to each other. These 2 orbitals are perpendicular to each other. Again, these 2 are also perpendicular to each other. The 2 electrons occupying these 2 orbitals are further away from each other. Finally, you have 3T1G. Its relative energy is 0, only because you can tell the 2 electrons both occupy the T2G orbitals. So it's either XY and YZ, YZ and ZX, or ZX and XY. In each of the 3 cases, there's no delta O, so 0 delta O. And also, if you look at these 2 orbitals, they are perpendicular to each other. These 2, again, they are perpendicular to each other. DZX and DXY, I'm going to show you the picture, this one and this one, they are perpendicular to each other. They do not share the same plane. Therefore, the electron-electron repulsion here is smaller than the 3p cases. So again, we have a relative energy of 0 for this 3T1G situation. And then again, we have 4 energy levels. We'll be able to observe the electronic transition from this 0 to delta O, from 0 to 2 delta O, from 0 to 15b plus delta O. That's why in this transition metal complex with a octahedral point group, we will observe 3 peaks in the UV-Vis spectrum. And then if we have some numbers here, let's say B is equal to 800 wave numbers. Delta O is equal to 20,000 wave numbers. And then we can compute the 3 UV-Vis peaks. The wave numbers of the 3 peaks are simply from 0 to delta O, it's just 20K. From 0 to 15b plus delta O, that's 32K wave numbers. From 0 to 2 delta O, that's 40K wave numbers. And with the wave numbers, we can easily compute the wavelengths in nanometers. They are 500, 312.5, and 250 nanometers. The last 2 numbers are UV, ultraviolet. 500 nanometers, that's visible light. That means this transition metal complex will likely absorb visible light with 500 nanometer wavelengths. And how do we know what's the color of this? It's pretty simple. Actually, if you remember 3 numbers, red 680, yellow 580, blue 480, and you can tell this 500 is between yellow and blue, so maybe it's greenish. And then remember, in this UV-Vis spectrum, the transition metal will absorb this green light with 500 nanometer wavelengths. And then if you shed a visible light, well, white light, natural white light to this transition metal, it's going to absorb the green light. And then the color of the transition metal complex is red. Again, if the complex, the transition metal complex, absorbs yellow light, it will look purple. If it observes orange light, the color of the transition metal complex is blue. All right, in the end, I'm going to quickly talk about the B. Typically, B is from 700 to 1300 here. And I intentionally gave you a smaller than the typical value. The average is 1000. I gave you 800. Sometimes B can be smaller than the average value. When does that happen? So again, B accounts for the electron repulsion. Remember, especially, if you have two d orbitals that share the same plane. So for example, this two. And then how can we reduce B? It's very simple. If somehow we can delocalize this two d electrons to the surrounding ligands, and then we'll observe less electron repulsion between these two d electrons, one occupying this orbital, the other occupying this dz squared orbital. So again, if you have a large ligands with a conjugated system, or you have simply something like I minus, adido, bromido, chlorido that can delocalize, can help delocalize the d electrons, you will observe smaller b values. And again, I just talked about the electronic transition from 3F to 3P. We observe 4 different energy levels, and because of that, we observe 3 UV-Vis peaks from the ground electronic state to the 3 excited states. And we were able to come up with the expressions of the wave numbers of the 3 electronic transitions and convert those wave numbers into the wavelengths. And we say if the transition metal complex absorb the green light from the natural white light, and then this transition metal complex has a red color.